Today we continue our work on the Elna programming language and its compiler, and we are going to do some improvements to the intermediate representation. And at first, let us look at the instructions. So we need TAC operator, and the first instruction that we are interested in is this read instruction. And basically the read instruction from the 3 address code is just converted to the assembly read return instruction, but we want that the TAC 3 address code return instruction does a bit more. It should be possible that read takes a value and returns this value. Because what is actually done is that if the procedure needs to return something, that the code generated is that we take a temporary variable, and these temporary variables are hard-coded. So we take this a0 variable, assign it some value, for example 0, and then we call read. But instead, this is 3 address code as it is generated now. And what we actually want, we want that return just takes one argument, one operand, and generates the proper assembly. Actually, let us look at generated assembly. For example, we define a simple procedure. Let us call it f, and everything this procedure does is just returning 0. Then we compile it. And then in the top half of the screen we open, or let us use the bottom half. It's then in build valid. This is stage 16 CLS, and we look for the F label, and F label. So there is stack prolog and epilogue generated for each function, but it is actually what I mean. 0 is assigned to T0, x5 is T0, then T0 is copied to the A0, I think x10 is A0, and this is the return value. But actually I think that we can make this thing shorter and just generate this one. So replace 2 instructions to generated instruction with a single one, and we will try to achieve it today. So we can remove this f function again. We don't need s anymore. Let us just look where read is used. call operator. I think, yeah. So it is the conversion to assembly. We don't need a return instruction is generated here. So basically, when we go through the definition of the declaration, we just always generate a return instruction at the end. I think that the best way to generate it is just to generate it when we see the return statement. Basically, our programming language can have only one return statement at all. This is the same as Oberon does it. So basically, you return statement in our language can be only the last statement in the procedure. So we can just, if we see the return statement, then we generate this return instruction, and afterwards we can just check if the last instruction is return instruction, and then it is not. We can still generate a return instruction without an operand, or we just let it be and generate it later in the when we generate assembly. So we need TIC return statement. It is the function that handles return statements, and what it actually does, it creates an assignment, and it assigns basically the expression in the return statement. This is this return expression. It converts it and it assigns it to the temporary variable 11, and this 11 and this 11 is I think a 0. Instead, we want to generate another instruction, so we want to generate elna TAC instruction create, and the instruction is the return instruction, and this return instruction will have a single operand. So we set the operand to this instruction, the first one, to this values. We handle the expression here, and we can just assign the values from this expression, yeah. On type operand value and operand length. It's actually long. If I compile it, it should have no effect because it is overwritten by the next instruction. So it compiles, but actually concatenation is fine. So we combine the instructions generated for the return expression, and then the return statement itself. If we remove this part here, then I suppose that the compiler will crash. So this is the first step. The second step would be just to look TIC operator red, and here we create the return instruction in the RTL. This is not what we want. We want to load the value of the first operand into the A0 register, and I had somewhere a procedure which can do exactly this. This is this one. So when we see the return instruction in the 3 address code, then we load the value of the first operand into the register A0. The only thing that we have to do is to combine these two things, the operand and red here, but operands can be probably empty. Actually, we can check this. We just check that if operands is empty, then we just write the result. If operands is not empty, then we set the next value in the list. Instruction list set next of operands to result. Then we have to set the next this one, next instruction. This is the last instruction in the list. We set it to the result since it's the last expression, the actual result. The first instruction in the list is then operands, and we can end it here. It will still fail since we don't generate a return instruction anymore. So if I look at the generated assembly once again, it's even not there. Valid state CL. Okay, this assembly is empty. We can look at the previous stage. Boot stage select CL. But this is the stage created by the this is the assembly generated by the previous stage, so it isn't what we need. I'm looking if I did a mistake somewhere. set the result as the next element of the operands, but I don't create a result in this section. So what we actually want, we want always to create the return instruction, and if operand is 0, then this is fine as it is, but if not, we have to use operands as the first element of the list. So we assign operands to result and next instruction is result. We try to compile it once again. At least the validation, the compiler should crash. It's fine, but at least this validation code shouldn't be actually empty, I think. Problem may be that if it gets a return statement without an operand, when we have a problem, since it will try to compile the first operand, by the first operand will be garbage since it is not set. So that means that we shouldn't generate the red instruction automatically, since it will break the assembly generation. It should still crash. Or it hangs. That can be the case as well. So if I look at the assembly now we have at least the generated assembly, and if I look at returns, so let us just take some procedure, find some procedure that doesn't have a return statement. We can actually again define one. So we just define an empty procedure and try to compile this, and when then we will look at the generated code. It generates the return instruction at the end, but what actually happens that it generates a prolog, so it allocates stack, but it doesn't add an epilogue, and this is actually the problem why the compiler hangs. So the assembly epilogue isn't generated anymore. I think actually epilogue is generated when we write the assembly, the RTL operator return. Exactly. This is the procedure that writes RTL instructions. So basically, if it sees the return instruction, then it writes the epilogue. So we have this RTL procedure declaration, and it basically compiles the body the question is where we add this epilogue generation. What is the best solution? Actually, I think that we should generate a return instruction. So in RTL, yeah, we need to generate an RTL instruction for the return. It shouldn't be that bad if we just duplicate the return instruction. So the problem will be if I add another return, then it will be generated twice for procedures that already have a return statement. So let us find where we generate this return instruction. So it is only generated if we encounter this LNATSC operator return. And it is RTL instruction, so we just create another one instruction. So let us call it return instruction, and we assign this value to it. Return instruction, and we append this return instruction to the body, so to the list of instructions. I don't know how this concatenate function is called. So instruction list concatenate, and the first argument is basically the body, and the second argument is return instruction. It also is possible that body is empty, probably, so that it is null. Yeah. Would be interesting to see how what the assembly looks like. I removed the flag function. But why? So basically let us look at the normal procedures. It just generates one return instruction as it should. And this function have epilogue at least, so if I do f again and then compile it, exactly. Actually, this problem is fixed then. So if we have an if function, the stack is allocated, and the stack is allocated afterwards. body is null, then we set body to the return instruction, and else we append the return instruction to the body. But we still have a problem somewhere. What happens if I write return 0 in here? Yeah, and that's the current problem. So I was wrong. If there are two TIC return instruction, then not the return instruction is generated twice, but the assembly prologue, and of course it breaks then the whole stack, and this is the reason why our compiler crashes. So we have to find a way to generate the return instruction once. Actually, I think that we just shouldn't generate the return instruction if we see the TIC return instruction. So here basically we always generate this return instruction, but I think we should just let it be. So we remove it again, and we copy the first line, and we just say that this is the result. So if we see the return instruction in the 3 address code, then we don't generate the return instruction in the assembly, because these things are different. So we just write the value of the operand into A0. This is the register there where the return value is expected to be, and we are going to look then at the procedure that generates the assembly for the declaration, for the TIC declaration, and we just insert automatically return instruction at the end. So we are going to look at, I think it was procedure declaration. Procedure declaration was that function, and here we have this return instruction, so we do it already. Okay, that looks fine, I suppose. But our problem was actually this one. And it actually looks correct as well. So we assign it to result and we say that we want to add the first operand into the register A0. What we actually can do, we can compare the assembly generation and just see what is broken. So we only did a small change. We are going to exit, then we generate the assembly. We save the assembly file somewhere, so it's built valid stage 16 CLS, and we call it new s. Then we stash our changes, so we do git stash, and I think new s is still there. This is the working state of the compiler, so we compile it again. And we compare now currently generated assembly with the build valid stage with the previous version, and I think we have to swap the arguments. This is CLS with new s. So it seems that a lot of procedures do not have an epilogue. For example, this one here. So we open the file again in the editor and look for the procedure. I don't need the file itself, I need actually the generated assembly. So it is stage S, and we look for this thing here. Variable declaration get type. What was it? Oh, these are my automatically generated getters setters for the records. But I think it's not the only problem. Right, okay. There were probably some other changes. Label numbers. The problem is basically if we look for the same function in the new file now, then we will find that it doesn't have a prologue, but it generates an epilogue. Okay. So we generate the epilogue each time. Then we see the return instruction in RTL. I think this is the only case. And what changed is that we need our previous changes. RTL operator read. So here we don't generate the return instruction, but we generate a return instruction in this case in procedure declaration. Actually, we shouldn't do it for this automatic declaration, since they don't have any stack. Alter procedures. Interesting. TIC record. Tag procedure declaration. Do we have something like this? So we can actually look for get, I think. No, this is not. Exactly, this is the function that generates these getters and setters, and it basically creates a declaration. So it uses this TIC accessor function, and TIC accessor creates a declaration. An instruction declaration. We probably have to save in the declaration whether we have a stack located or not. So it has the next declaration in the list. It has a name. This is procedure name and name length, and body is the list of instructions. And we can actually just introduce an additional parameter, and these successors are generated already successor during the 3 address code generation. So let us see where this thing is created. This is not this. That's not it. Attack global declaration. This is the place instruction declaration size. But this is the RTL declaration. I don't think. Declaration. TIC procedure declaration. Basically, in this case, we have set stack. We have stack, so we can say that result stack is 1, and in the another case, when we have these accessors in here, we create a declaration here too, but we don't have any stack here. I hope I wrote it correct before. Result is probably a pointer to pointer. Yeah, result is passed as parameter, and therefore it's dereferenced here. So let's just look for the set stack. Yeah, here it is fine. It is just a pointer and not a pointer to pointer. So we still need a return instruction in the RTL, because the assembly still has to return. So it should jump to the caller, but the problem is that we shouldn't generate the epilogue. So let us see. this is the place where the instruction kind, where we generate the assembly, and I need just more data here. Instruction kind is just not enough. So I'm going to split the screen once again, and I will navigate where this thing is called instruction name. Write instruction. Here we write a single instruction. It is still not enough. Probably the easy solution would be just to go to the writer that writes the declaration. Instructions, and this one is called from here, and here we have the declaration, so we can see whether this declaration has a stack or not, and it also writes the read instruction here. So we can pass this stack argument to the other functions so that they can write prolog or epilogue, or we can just generate this thing here. Let us introduce a local variable hasTag, and we say that hasTag is Elena instruction declaration get stack from procedure, and we say that if hasTag, then we write the epilogue here, so we can remove this line here and we move it in here. And the compiler still hangs. It is actually RTL. We have to copy this stack value from TIC to RTL. So we will have RTL procedure declaration, and actually it will get the name from TIC declaration and copy it into the RTL declaration. So once again we define a local variable hasStack, and we assign the stack value from TIC to this variable, and we just assign it to the result. important is, of course, to set the correct variable and not the length. Okay. Basically it says that it doesn't have a new line between return and the epilogue. And now it works finally. I don't like this solution that that I write it in here. Let us just remove the code that we don't need anymore. For that I need to look into git diff so I can see where I added comments, and the one case is 1137, so we can open this file 1137. This comment can go. So what else? Then we have this epilogue here. I let it be here for now because we generate the prologue in this procedure, but the epilogue in the other procedure, and it's not very nice. We should unify it somehow. This one is fine, and that's all, I think. Okay, we have the return instruction in here, so we should fix it as well probably, but otherwise write the epilogue. We don't have this return instruction here anymore, so let us remove this one. Where was it? 2462. This is this assign instruction, so we generate return instead with the operands return expression and first instruction. That looks fine, I suppose. So the stuff here, and first instruction is returned at the end. Yeah, that looks fine. And this epilogue, write the epilogue. Yeah, here we generate F3 address code procedure declaration, and we don't write the return instruction automatically, but we write the start instruction automatically, but which we don't actually need this start instruction, I think. I mean, I have a similar instruction, allocate stack, for the allocate stack for the RTL, but I don't really need it for the TIC operator. I would be interested what I do with this thing. So if I see start, then I write it to the allocate stack. And if I don't see start, that then there will be no allocate stack instruction, and it wouldn't generate this stack anymore. Basically, if we do it symmetrically, we should also remove this one. It will break. Probably my accessor functions, this is probably exactly what they do. They just don't generate this first start function, start instruction. So the first instruction that they generate is basically directly the add instruction, probably. So before we write the body, here we write the procedure name, so the label basically, and what we probably can do is just check for the stack setting once again, and if the procedure has a stack, then we can generate this thing here. It would mean that return instruction in RTL and the allocate instruction are not used. And this is kind of stupid. I really don't like it. I think I should pass just the stack size to the writer instructions so it can use this parameter. Let us write this way. I don't like that I don't have allocate stack and return instructions. So let us pass the hashtag variable in here. So then we go to the instructions procedure and we allocate the variable here. On the other hand, of course, we can just it doesn't mean that we don't have them. This is basically the first and the last instruction, and we know it because each procedure starts with allocate stack instruction and ends with the return instruction. So we can I'm just not too sure how to do it. Yeah, basically we know that body statements start with this with allocate stack instruction and add with the return instruction. It is just so that we ignore these instructions and just don't generate anything for them, but they are still there, I think. Okay. I wonder if I can say that instruction get next, so that we just skip the first instruction. No, we can't. This skips the new line somewhere. Why did it work before? It works without the new line here. Because this thing always write a new line. Even if I don't write any code here, there is a new line written afterwards, so the new line is added automatically because it basically sees the allocate stack instruction. Would be just interesting to see if our first instruction is always an allocate stack instruction. For that we are going to take the second. This is actually the first. We can just get the kind. This one instruction get kind, I think. Can it be instruction get kind? I think exactly. Elna tell instruction get kind, and we get the kind of the first instruction, and first instruction is body statements, and we just see if it crashes or not. Probably not. And we just say then if x is unequal elna RTL operator, allocate stack, then just print something as comment in the resulting assembly, then put a new line and enter string there. And now we only need to look at the generated assembly, so and just look for this ISDF, and it isn't printed anywhere, so actually allocate stack is always the first instruction. The other thing that we want to check, we cannot check the last instruction since it is a list, and we do not want to go through the through the whole list. I actually want to introduce a new list data structure, so it saves the beginning and the end of the list, because it would be easier to add new elements to such a list. But this is not the case currently, and we do not have the last element, so I won't be looking for it. I think that we just let it be. Yeah. So we don't need this thing anymore. We don't need this x variable anymore. We'll try to compile it, and if we see allocate stack, so what we are going to do, we just add a comment here. We make an else of it, and we add a comment here that the value here is expected to be allocate stack or that. We set the argument count to 0, and we remove everything else. And we need to write else properly, of course. Okay, that looks fine. Could we achieve something in the code generation? I think actually no. So we try to generate assembly for this function once again, and just to see what it does. No, it does actually the same as before. The new lines here are not that bad, so I can see actually the space between prologue, epilogue, and body. Yeah, the value is still safe in X5, and then copy copy it to the X10, unfortunately. Let us save this assembly once again. So we copy build valid stage section CLS into new S, and then we stash our changes and compile the old version of the compiler, and we look whether the generated code has changed or not. So we make div nur again, and we compare the old compiler, so stage section CL with the new. It's not identical. Yeah, there is a lot of new lines, and this is probably everything. So okay, labels changed. No, I don't see any significant changes. There are some changes because we changed the procedures and things like that, but I don't see changes in the code generation itself. Another interesting thing would be to look why this operand value still writes the value in x0. Load operand value, this is the function that we call, and we pass the into value in here. And what it actually does, if it sees an immediate, so a constant value, this is the case here on the top, then we just should load immediate in this register. It should actually work. I don't understand it. Let us look at return statement again. Return statement. So when we visit return, we compile the expression in this LNTIC binary expression. It should basically just return nil for the first instruction, and it should save type immediate value 0 into these variables. Then I say that I generate a TIC instruction and I assign the return value to this instruction, and then I return the generated instruction plus plus this return instruction. And then when I see this KC operator read in here, do I need this start instruction? Kind of. This can be removed as well. Basically, I just say a print value return and write this, and this is A0. Stack. Actually, I add the return instruction here automatically, and I can do the same for the first instruction. So I can actually say that return instruction is elna rtl instruction create elna rtl operator allocate stack, and then we can say that elna tail instruction, was it set next instruction set next instruction rtl instruction set next, and for the body, and we set the returned body to the next instruction after this allocate stack instruction. So return instruction followed by the body, then we say that body is return instruction when we allocate a new return instruction, and at this point we know that the body is not empty actually, so we don't need this check anymore. We can just append this instruction to the body and look what happens. Set a prompt elna rtl instruction create. Let us look at this procedure, and it calls elna instruction list set next. No, this is wrong. Set next, it was here, elna rtl instruction list without rtl, I think, elna instruction list set next. Now we can go to this elna tac operator start, and we don't need this one anymore, I hope. First instruction, it is used here. Okay. First instruction can probably be empty. Yeah, no, it works. So we can move this, write the prolog comment to, we'll keep the comment. The comment is nice. We just write epilogue exactly, and this one can go as well, and this one can go. So, and we did it, so we don't need this start instruction anymore. If I remove this case, then it still works. Oops. And now we can just remove the instruction that we don't use anymore. Okay. We still simplified the instruction set a bit, so we removed the unused start instruction in our intermediate representation, and we made the return instruction useful, so it returns a value now and isn't just an empty instruction that doesn't anything. And we probably will look at a later point how we can optimize this thing further.